Hello everyone, and welcome to our ECE 492 final presentation and demo. My name is Cole Milburn.
I'm Nick Dioxin. I'm Jonas Wong. And I'm Elman L.
And our project is the Direct Time of Flight, D2F for short, imaging system sponsored by our client, Dr. Masum Hossain from the University of Alberta. The issue we wanted to address with this project is that many sensor systems capable of laser scanning and imaging may be largely complex, inflexible, and can lack portability. Our solution was to develop a portable, all-in-one D2F imaging system capable of processing and visualizing real-time object information on a relatively compact form factor. And after 3 months, multiple design changes, and some social distancing, our team has created a prototype system that meets all these design requirements. We'd now like to demonstrate the key functionalities and features of our prototype design.
The overall system is comprised of three major components: time-of-flight evaluation kit from Analog Devices, a Raspberry Pi 3 board, and a Zybo Z7 FPGA development board from Digilent. The Zybo Z7 board is the main point of contact for the user. They will use the onboard peripherals of buttons and switches to interact with and configure the system. The FPGA board connects to an external display via the HDMI output port for visualizing the collected data. Additionally, the board connects to the Raspberry Pi 3 board via a USB cable for serial data communication, as well as for sharing the power supply to the Pi. An OLED display is also connected to the Zybo board through its available GPIO to support user interaction by displaying informational messages about the system. Finally, the evaluation kit is used to carry out the DTOF process by emitting pulses of infrared light and measuring the time differences between light being transmitted and reflected to reduce an infrared image of the scene, as well as to calculate the distance of the target object.
Before initiating the system, the user may also configure it by toggling the rightmost switch. Here, the user has some options for setting their distance threshold detection value, the number of data frames they'd like to collect, and the detection range of the system. By default, the distance threshold value is 0, the number of data frames to collect is 1, and the detection range of the system is set to medium, which denotes a range between 1 and 4 meters. The user can use buttons 1, 2, and 3 to increase the configuration values when switch 1 is toggled high, and to decrease them when switch 1 is set to low. For the purposes of our demo, we'll set the distance threshold value to 2 meters, which means we'll be notified when an object is detected at most 2 meters away. Additionally, we'll set the number of frames to collect as 20, and we'll leave the system's detection range at medium. When we're done configuring the system, we can exit the configuration state by toggling the rightmost switch back to 0. Let's now initialize the system by pressing button 1. When in the initialization state, the Zybo board will talk to the Raspberry Pi and tell it to initialize the evaluation kit to prepare it for data collection. Once initialized properly, the Raspberry Pi will collect our specified number of frames and subsequently transmit them to the Zybo board, where they can be stored and further processed. Here we see the raw frames of data collected from the evaluation kit being continuously displayed one after the other. We note that by default, the images are shown as infrared due to the nature of how the data is collected. On the top left of the image, we can also see a numbered value being displayed for each frame visualized on the screen, which represents the measured distance of the target object. We can see that the value decreases as I move closer to the system and increases as I step away from the system. We can also see that the numbered value is being displayed as red whenever the target object is within the distance detection threshold that we set during configuration. Right now, the image frames are being displayed one after the other in what we call normal streaming mode. By toggling the rightmost switch, we can change the streaming mode to slideshow to now have control over the visualization process. From here, I can continuously press button 1 to increment the frame as if it were slideshow. This is useful if you're looking to analyze certain frames in more detail. We can exit this mode by toggling the rightmost switch back to 0 and then subsequently pressing button 1 to start streaming normally again. We have also implemented two simple image filters to showcase the close to real-time performance of the system. The first filter is a point processing filter that simply complements the pixels of the image frame. This filter can be turned on and off by toggling switch 2. The second filter is a neighborhood processing filter that detects the edges of an image. This filter can be turned on and off by toggling switch 3. Lastly, because we didn't show it in our demo, here are the image comparisons between the different detection modes that the evaluation kit may be initialized with at the start of the system. The near mode detects objects between 250 and 800 millimeters, and the far mode detects objects between 3 and 6 meters.
Most of our functional and performance requirements specified for the prototype system were achieved in our final implementation. We are able to successfully interact with the evaluation kit to request that the data be collected then transmitted for further processing, and from there, we're able to process and visualize the collected data onto the external monitor using the Zinc 700 system on chip. Additionally, we were able to successfully implement a distance alert system that would allow the user to set a customized distance threshold value, as well as notify the user when a target object is detected within the provided threshold. We were also able to implement some simple image filters that could be used to further process the collected data before being visualized to the external display. Finally, we were able to successfully implement the majority of the system as a bare metal application, which means that all of the aforementioned tasks on the Zybo board are handled without the help or overhead of an external computer, operating system, or kernel, and is instead carried out by a minimum amount of resources made up by the programmable logic and processing system partitioned of the Zinc chip.
Originally, we planned to integrate the Zybo board and evaluation kit directly together and not rely on the third Raspberry Pi board, but we didn't get the necessary documentation from Analog Devices in time to confidently interface with the evaluation kit's processing chip using the Zinc 7000 system on chip. Because of this, we opted for using the Raspberry Pi for fetching the front-end data and communicating it back to the Zybo board serially via its UART interface. This created a bottleneck in the system's processing scheme, as the UART interface is not nearly as fast enough to transmit large amounts of data required for even a single frame, which meant that it would be much more difficult to implement a live visualization process that would be supplemented by a continuous and fast stream of data from the evaluation kit. Ultimately, we opted for continuing with the UART implementation and added the functionality of storing multiple frames of data to be continuously displayed to emulate the visualization process of an ideal system.
Some ideas for future work would include building off of the foundation we've set in our prototype. This would first include improving and optimizing parts of our project that work, such as increasing the granularity and accuracy of the measured distance values, as well as for integrating the evaluation kit and Zybo board directly with one another to be able to quickly and reliably stream data in a manner that better aligns with real-time performance. Additionally, implementing features that may have been scrapped or were not completed on time during the development of the prototype would also be nice to implement in the future. An example of the missed feature would be the ability to save and record image data to an external memory device like an SD card. Finally, given extra time and resources, implementing a relatively simple convolutional neural network for object recognition will be an added bonus that would nicely complement the already implemented object visualization process of the system.
Overall, this project has been a challenging but extremely rewarding experience, and we believe that our developed prototype has built enough foundation to now be freely tweaked and used for a variety of applications. We'd like to thank Dr. Hossain, Dr. Knudsen, and Raju Makopali for their continued guidance and support throughout the semester. With all that said, we'd like to conclude our final presentation and demo and open the floor up to the audience for any questions. Thank you very much.